All right, so we're going to do an example, or actually an activity. So I'll guide you through the activity, and then we're going to do an example after this. So the question here is, if we let our set P, which is the set of all people, and if I understand that people are getting born at every minute, so fix a time, set of all people in that time period. So it's a fixed set. Um, we want to know is the relation has the same birthday as, which is a relation on the set of all people. We want to know is it an equivalence relation. Okay, so is it satisfy the properties of being an equivalence relation? So to do that, we need to ask, is it reflexive? So this means, does a person have the same birthday as themselves? Is it symmetric? That is, if person Bob and person Alice, if person Bob has the same birthday as person Alice, does person Alice have the same birthday as person Bob? And we have to ask a similar question for transitivity. So if person A has the same birthday as person B, and person B has the same birthday as person C, is it true that person A and person C have the same birthday? So I'll let you think about that. We are going to do this example, though, on triangle congruence. So we can specify where the triangles are being congruent, and this is in the Euclidean plane, so the xy plane. You can think about triangle congruence on um, uh, any shape, but for this problem, we're just going to do the plane. And we have to ask the following questions. Is it reflexive? So is a triangle congruent to itself? And the answer is, well, of course it is. It has matching angle measures and matching side measures to itself because it does, because they're just equal. Is it symmetric? That is, if triangle T is congruent to, sorry, T1 is congruent to T2, does that imply that T2 is congruent to T1? Well, of course, because if they match in this order, they're certainly still going to match in the other order. So yes, it's a symmetric relation. Is it transitive? So T1 congruent to T2 and T2 congruent to T3 implies T1 congruent to T3. Well, certainly, if T1 and T2 have matching angle measures and side measures, then T2 and T3 have matching angle and side measures. Well, then T1, which matches T2, which matches T3, will have matching angle and side measures. So certainly. So triangle congruence is an equivalence relation on the set what? So what's our set here? Well, T is going to be the set of triangles in R2, the Euclidean plane. And we've just shown that it's an equivalence relation. Great. Now, I want to observe something about the congruence relation here. The congruence relation is not equal to equality. These are different things. Namely, you can have triangles which are congruent but occupy different points in space. And so they're not equal triangles, although they are congruent triangles. So this is a weaker notion than equality is because there's more things that are congruent than are equal. And in geometry, what you do is you regard congruent triangles as being essentially the same triangle, as being equal or as being the same, and we're seeking to do something like that, but with algebra, and we're going to get to exactly, well, we're going to get to our first example of this pretty shortly, where we're going to think of sort of Z as the set of all triangles. So Z is our big set of all numbers that we're working with. And we don't want to look at equality. We want to look at sort of a weaker notion, which is going to be some congruence relation that we're going to put in the next video.